Okay, so the next talk will be given by Angel Barria Comicheo, and he will talk to us about some spectral perturbation results of complex and self-adjoint operators over a Hilbert-like ultrametric space.
Thank you, Professor. Hello, everyone. Good morning, good afternoon, good evening, good night. I'm Angel Barria. I'm talking to you from Winnipeg. First of all, thank you for the invitation and to say that this is an honor to be here with so many legends in non-Archimedean analysis. Wow, it really is a lot to be here. Okay, today we'll talk on spectral perturbation results of compact self-adjoint operators over a Hilbert-like ultrametric space. So I will start giving a brief description of the fields that we are going to use a base field, then a brief description of the Banach space we're going to work on, and then a brief description of compact self-adjoint operators in this space. And lastly, I will talk about the problems and results that we are having in spectral perturbation theory. So let's begin introducing the fields R and C script. So as in case you didn't watch the previous video or the previous presentation, the Levi-Civita fields and the complex Levi-Civita field as are fields of functions from rational numbers to complex numbers or real numbers with left-defined support. But in the same way as p-Adic numbers can have a power series expansion, and the elements of the Levi-Civita field also can have power series expansions, and I in this opportunity will introduce the R script and C script as these power series fields, where the power series have coefficients in either real numbers or complex numbers, and the exponents form a strictly increasing sequence of rational numbers that is divergent. The evaluation of these elements is simple to define. It will be always e to the power of negative t1, where t1 is the first exponent in this power series expansion, or in other words, the smallest, the minimum of the support of these functions. So very quickly to say that these fields under this, using this evaluation, they become non-Archimedean value fields that are Cauchy complete in the sense of metric spaces if we consider the metric induced by this valuation. There is some analogies between these fields and the real numbers, complex numbers field. As you can see, any element in the complex Levi-Civita field can be decomposed into a real part and imaginary part times I, where I is the root of one of the roots of x squared plus 1. And the evaluation will satisfy this nice property. The evaluation of an element of Z will be equals the maximum of the evaluations of the real part and imaginary part. The involution, defined in this way, mimics what happens in the conjugate operation in the complex numbers and satisfies the very nice properties that we would expect in the complex numbers. Although here, for example, the product of an element of the complex Levi-Civita field times its conjugate will be not a real number, but a number of the real Levi-Civita field. And another property is that solidifies the analogy between these fields and the real numbers and complex numbers is that R is real closed, meaning that it's an ordered field where every positive element has a square root, and every polynomial of odd degree has at least one root in the field. And if you consider the extension, if you add one extra element, one of the roots of x squared plus 1, you obtain automatically the algebraic closure, which is precisely the complex Levi-Civita field, which means that every polynomial in this with coefficients in this field will have n roots, all the roots in this field. Regarding the Banach space we're going to use, I suspect that everyone knows what is the space is 0, the space of all the null sequences with components in this field. If you consider any sequence in C0, naturally you can decompose it into an imaginary part sequence and into a real part sequence, X and Y. And the norm for this space will be the supremum norm, the supremum of the absolute values, supremum of the evaluation of the components, which since these are null sequences, the supremum is attained, so we can talk about the maximum. And happens that the maximum, the norm for a sequence in C0 will be the maximum of the norms of the sequence of real parts and the norm of the sequence of the imaginary parts for the sequence set. The proof that this space with this norm is Banach is a standard, is identical to the classical case when you work with real numbers or complex numbers. So we will be working in this Banach space. Here is where the interesting part starts. Narici and Wittgenstein in 2005, in a publication where they were studying inner products on this space, they find out that this formula is a good candidate for an inner product on C0. It's well defined because in a complete non-Archimedean value field, if this general term goes to 0, then the whole series goes to 0. Is convergent. If the general term goes to 0, the series converges. So it's well defined, it's well behaved. Is linear in the first component, behaves well with the conjugate operation of the field, the complex Levi-Civita field, is continuous with respect to the norm. This is very easy to see. Let me show you. The definition, this will be this convergence series. And here, since the evaluation is non-Archimedean and the series is convergent, this will be the smaller or equal than this maximum. And of course, each of these is going to be smaller or equal than the maximum of the whole vector. Right. So there you have it. Property 5 is satisfied. Property 6, if you multiply, if you compute the inner product of a vector by any other vector and always the result is 0, that means that the original vector has to be 0. This means that all the functionals of the form of this form will separate points on this Banach space. So all these properties can be proven on C0 with this inner product under any non-Archimedean value field that is complete, Cauchy complete. The last one is the novelty. The last one is not always true if you change the field, the scalar, the field of the scalars. So Narici and Bekenstein learned that, and they published this, that if the residual class field of the field of scalars is real closed, then this equality will hold. Okay, so for us, the Levi-Civita field has residual class field equals to the real numbers field. So this equality works well for the Levi-Civita field. And once that is proven, it's not difficult to show that this also is true when the scalar field is the complex Levi-Civita field, which is our case. Why I say this is interesting? Because if you see here, we have a Banach space under a complete, over a complete field, which norm is induced by the inner product. In the classical terms, we will be talking about Hilbert spaces, right? So that's why we call this a Hilbert-like ultrametric space. The problem is the similarity is rather superficial. There are many reasons, important reasons why we cannot use the same results of the Hilbert spaces here. First of all, it's not orthomodular. This means, for example, you have a non-trivial subspace that is closed on C0 that doesn't have an complement, ortho complement. Another of the reason is that, for example, in a Hilbert space, the dual of a Hilbert space is isomorphic to itself. Here, we know that the dual is L infinite, so that fails. And more generally, in the classical case, the Hahn-Banach theorem holds for any Banach space, and here in this particular case does not hold in C0. Why? Because the field that we're working on is not spherically complete. Of course, if we change the field to the Hahn field, for example, or any other spherically complete field, then the Hahn-Banach theorem will hold, but we don't solve the other two problems. So these already tell us that things on C0 doesn't work as we expect. So how much can we recover? Does it work to work here? Let's see. So let's consider, so this is for notation purposes, let's consider the standard Schroeder basis of C0. And let's consider these functionals, the functional that takes a sequence in C0 and gives you the jth coordinate. This functional has length 1, and the norm of every vector here can be written as the maximum of the evaluations of these images, which is the norm of X will be the maximum of the evaluation of the components. Okay. Now let's talk about operators on C0. Let's consider LC0, which is the collection, the space of all the continuous and linear operators from C0 to C0. This is a Banach space under the standard norm, defined in this way. And this norm is non-Archimedean, so satisfies the strong triangle inequality. And just for completion here, I need the definition of self-adjoint operator that in this context is just an operator for C0 to C0, satisfying this equality for every vectors X and Y on C0. To define compact operators, in non-Archimedean context, we cannot say that the compact operator is one that the image of the unit ball is pre-compact, because if the field is not locally compact, then a compact the image of a unitary ball, if it's compact, or if the closure is compact, then that would be only the singleton. I mean, the only compact operator using that definition would be the zero operator. So in order to avoid that, the concept of precompactness has to be linearized. That is how the concept of compactoid was born. However, we will not teach this completely in this talk. I will not give more details about this. For completion, I want to give you the proper definition for a compact operator in the non-Archimedean context. If you have an operator from one norm space to another norm space, we say that it is compact when the image of the unitary ball is a compactoid and when behaves as is expected from a compact operator in the classical case, which means you can approach this operator using operators of finite rank. This means for every epsilon, there will be an operator of finite rank that is close. I mean, the norm of t minus s will be smaller than epsilon. And more explicitly, an operator t is compact if and only if there are vectors and functionals for which the partial sums of the tensor products converges uniformly to the operator t. So basically, if we can write operator t in this way, using operators in this form, then the operator will be compact as is expected and as is usually the case in the classical case. So basically, we'll be using the notions 2 and 3 for this idea for today's talk. Definition. If you consider an orthonormal basis for Cn or C0, then we say that an operator or matrix is diagonalizable when the corresponding matrix with appropriate orthonormal basis, the representative matrix is a diagonal matrix, or in other words, if the operator can be written this way, where these alpha i's will be the eigenvalues, and these tensor products will be these functionals times the vectors of the base. I need this definition now because I will need this this notation. The operator EI is given here, and I will use it now. So what do we want to do? What is the objective of this research project? We want to show that every compact self-adjoint operator on C0 is diagonalizable. In the same way, in a Hilbert space, every compact self-adjoint operator is diagonalizable, even though they can extend the result to normal operators. We want to prove this on C0. If we start playing with some concrete specific operators that are compact and self-adjoint, we realize that these are diagonalizable. So there's after some experience, trial and error, there is a hope that every compact self-adjoint operator in C0 is diagonalizable in the non-Archimedean context. So when I first start tackling this problem, I try to adapt the classical result, the classical proof of diagonalization of these operators in the classical case to the non-Archimedean case. But I found problems. So for example, one of the tools used is that the spectrum of any compact self-adjoint operator is not empty. And this is in the classical case is proven using the Liouville's theorem. And if we try to mimic that reasoning, the problem is that Liouville's theorem holds in the non-Archimedean context for functions that already has a power series expansion. But in the Levi-Civita field, if you have a differentiable function and a random, an arbitrary differentiable function, we don't know if it admits a power series expansion unless we add extra conditions. But to prove this theorem, we need the result to be able to work for any differentiable function. So how can we prove that? Something like that. How can we prove that any differentiable function admits a power series expansion? In the classical case, a key point of this to prove that is the Cauchy's theorem, which heavily depends on the connectedness of the complex numbers, right? When you have a loop and you can move it, form it continuously, what happens that in our case, non-Archimedean value fields always are totally disconnected. So that smoothness transformation gets lost. Another problem that we have with the classical ideas is that in a compact self-adjoint operator, these amounts, the supremum and these infimums, are examples of eigenvalues for these operators. The problem is that for the Levi-Civita field, even it is an order field, but we in this is a non-Archimedean order field, meaning cannot be detecting complete, meaning there are non-empty sets that doesn't have support, supremum or infimum. So these amounts might not exist for a compact self-adjoint operator. Maybe they exist, but so far we don't have no clue. So these difficulties show us that we need, if we want to prove this, the spectral theorem for compact self-adjoint operators, we need another approach. So I decided to use a different approach, and this is what I want to show you. I start digging into Diarra's paper published in 2009. It gives us matrix representations of linear continuous operators on C0. He says that every linear continuous operator on C0 has a matrix representation in the sense that the image of a vector can be retrieved, can be obtained as matrix multiplication, infinite matrix times the vector in column form. And the norm for this operator will be given by the supremum of the evaluation of the entries of this matrix. Furthermore, he gave a complete characterization of the matrix representation for compact self-adjoint operators. He said that an infinite matrix like this will represent a compact self-adjoint operator even if satisfies the following properties. First of all, is a Hermitian matrix. Second of all, each row and each column are null sequences. And third of all, the norm of the column vectors approach to 0, the norm of the row vectors approach to 0. And here, since this is a self-adjoint operator, is Hermitian matrices, means that the row vectors are the conjugate of the column vectors. And that means that the diagonals doesn't have an imaginary part. All the diagonal entries are members of the Levi-Civita field, are script, not C-script. Maybe the other entries are on C-script. Okay, taking this into consideration, I came with the following idea. So, given the form of the matrix that represents a compact self-adjoint operator, this matrix can be described as a power series where the coefficients are infinite matrices with entries in the complex numbers, and these infinite matrices are Hermitian. Also, these matrices are represent operators of finite rank, meaning that they support the non-zero entries will be here in a box, in a small submatrix on the corner, and all the rest will be zero. Notice the nice similarities between these operators and the members of the field. The members of the field are of the form AK, DTK, where the coefficients are complex numbers. If you replace those complex numbers by these infinite matrices with complex entries, then you have representation of compact self-adjoint operators. Okay, what do we want to do? In this convergence series of matrices, I will take the partial sums and I will work with them as operators of finite rank, and I will study them like this. So let's consider a compact self-adjoint operator T on C0. To simplify cases, let's work with the operator of norm 1. So the partial sums we saw earlier, from this sequence, we can define the partial sum as pk, the operator pk, or matrix pk. Given by the partial sums, here again the exponents are rational numbers in increasing order, and the matrices A0, A1, A2, etc. These matrices are matrices with entries in the complex numbers and are Hermitian. So if we compute the norm of the difference between T and these approximations, that will be governed by the evaluation of the powers of T. And we know as K goes to infinity, these valuation goes to 0. And this implies that these operators, which are self-adjoint and compact of finite rank, converges uniformly to the compact operator T. Having this setting, this is just a setting, having this setting, what is the idea? If we study the eigenvalues for pk, we might have information on the eigenvalues of T. So far, remember, we cannot know if a compact self-adjoint operator has an eigenvalue. We don't know. There is no proof of that any compact self-adjoint operator has an eigenvalue different than 0 at least. So when T is different than 0 operator. So now let's go to the results. Again, just for you not to forget what this symbol means, let's consider the following lemma. If you have a member of the complex Levi-Civita field that is not an eigenvalue for a matrix or of operator of finite rank that is diagonalizable, then the inverse of this operator is given by this formula. This is a very well-known lemma tool that the proof is quite simple. You just compute this operator with lambda I minus G, and this is a straightforward computation that will give you the identity. If you compute the computation on the other order, also you will get the identity. So that's a proof for this lemma. We will use it later. This is another result that I need. For this, I will show the proof. Let's consider two matrices or operators of finite rank. And let's consider an eigenvalue for one of them. Then either the eigenvalue is also an eigenvalue for the other operator, or you have this inequality proof. So let's X be a vector, an eigenvector corresponding to this eigenvalue. So what happens if lambda is not an eigenvalue for G? If not in a punctual spectrum of G, then that means that the matrix or operator lambda I minus G is inverted, right? So when we look at this equality, lambda I minus J of X will be F minus G X. Since the operator on the left is invertible, we can use it on both sides. So I will get this composition or multiplication whenever you're working with operators or matrices. So this implies that the norm of X, using the nice properties of a norm, multiplicative norm, we can deduce this inequality. And since the norm of X is different than 0, because X is not a 0 vector, you simplify on both sides and you get the inequality. Now, with these results, we're ready to prove one of the major key results that we have here in the non-Archimedean case. When we approach, when we compute the eigenvalue and we see the perturbation of the operator and the corresponding perturbation of eigenvalue. Consider two matrices or operators of finite rank and consider a eigenvalue of one of them. If that eigenvalue is not an eigenvalue for a diagonalizable operator, then there is one of these eigenvalues is close to lambda, as close as G is close to F. So we have this inequality allows me to control how close we can get the perturbated eigenvalues. When we use a self-adjoint or diagonalizable operator or matrix. The proof for this. I have prepared a talk with very short proofs, so everyone keep track of it. Let me see, I was here. So by the previous theorem, we have the following inequality. Right? If lambda is not an eigenvalue for G, then we have this nice inequality. Then because of the first lemma I commented here, if lambda is not an eigenvalue of G, this operator is invertible, and we have a explicit formula for the inverse. The inverse is diagonalizable and has this form. Now, here comes the main advantage of being on the non-Archimedean case, the strong triangle inequality. We use it in this addition, and we can say that one is smaller or equal than the maximum of these expressions. The norm of the operator EI is 1, so we can ignore it there. We have this. Once we divide this term, because none of these terms is 0, right? Once we divide this term on both sides of the inequality, we obtained the desired inequality. So as you see, very simple proof. However, this has very important consequences. Actually, this proof also, there's a version of this on the classical case in spectral perturbation theory, but there is some complications here. And this not always is true. This only can be proven in the case where lambda has multiplicity 1. That is in the classical case when you're working with real numbers or complex numbers. Here, in this context, the multiplicity of the eigenvalue is irrelevant. We have this inequality for any multiplicity of the eigenvalues. So again, I just put here again this corollary just to remind you what is the definition for BK and what is the relationship between BK and the operator T, to give a nice context for the next corollary. If lambda is an eigenvalue for BK, then there exists another eigenvalue for BK plus 1 that is close to the eigenvalue of lambda, is controlled by this term. So remember, if BK is defined by this form, BK plus 1, you can say that is BK plus a small perturbation of order dk plus 1. Sorry, tk plus 1, ak plus 1. Where ak plus 1, again, remember, is a matrix with entries in the complex numbers. So the evaluation of the entries in those in that matrix always is 1. So the order of this element is governed by the Levi-Civita number d to the power of t sub k plus 1. Let's prove this corollary. Proof. Let me keep the, okay, there. Proof. If, so there's two cases. If lambda is an eigenvalue for bk plus 1, then the problem is not a problem. We just choose tau equals lambda, right? So this difference will be 0 and the inequality is trivially satisfied. Now, in the non-trivial case, what happens if lambda is not an eigenvalue for bk plus 1? Then that means that according to the previous corollary that we just proved, there exists an eigenvalue for bk plus 1 such that is close to lambda. And the error, the distance, is controlled by the difference, the norm of the difference of these two operators. And as we saw earlier, by definitions of the bk, the distance is of the order d to the power of k plus 1. So yeah, again, that is a proof of the corollary in a few lines. So this tells us that we can start thinking of a sequence of eigenvalues of the operators bk that actually approach to each other. we can form a Cauchy sequence of eigenvalues in a Cauchy complete value field. Again, just in case you forgot, this is the definition for VK. This is the relationship with T. This is one of the accomplishments we have. For every eigenvalue, lambda 0 on the Levi-Civita field of A0, there exists a convergent sequence of eigenvalues corresponding to the approximations VK of the operator T, such that the limit of this has to do with the spectrum of T. For now, we can prove that it's an approximate eigenvalue. Let me show you. So remember, the compact self-adjoint operator can be thought as this power series of matrices, the T1, A1, plus the T2, A2, and so on. This is the compact self-adjoint operator. This result tells you that if you begin with any eigenvalue of the complex matrix A0, you can create, you can look at the eigenvalues of these partial sums and have a convergent sequence converging to an approximate eigenvalue of T. That is the idea of the theorem. So let's see the proof. So let lambda 0 be an eigenvalue for A0. So by previous lemma, for every k, we can find an eigenvalue of bk such that lambda k minus lambda k plus 1 is controlled by d to the power of tk plus 1. So this tells us that the Cauchy, the sequence of eigenvalues is Cauchy. Then this sequence is Cauchy on the Levi-Civita field, which is Cauchy complete. Therefore, we have a limit. It's convergent to some, let's call the limit lambda on the Levi-Civita field. What we're going to do, for each of these eigenvalues, we're going to choose an eigenvector of norm 1. Let xk be a vector of C0 of length 1 such that bk xk is lambda k xk, eigenvector corresponding to lambda k. Then we will show that this sequence approaches this sequence. So this norm, the norm of this difference approaches 0. This is what we're going to show now. The norm of t of xk, here we are going to add and subtract an auxiliary term, as always we do in these cases. Now we use strong triangle inequality. So this is smaller or equal than the maximum of tk minus lambda k xk, and the norm of lambda k xk minus lambda xk. you notice here, since the definition of xk is an eigen vector, we can replace that by bk xk. And here we can factor by the norm of xk. We have this nice factorization. And, oh, sorry, this is, I forgot to write the maximum of these two. So this less or equal than here using the properties of continuity. In terms of the norm, we have this. And remember that the vector xk has norm 1. So basically, you just can ignore the norm of xk. And you see that we know that bk approach to t. So this can approach to 0 as k goes to infinity. According to the definition of lambda, this also will approach to 0. So this approach to 0 as k goes to 0. This shows that lambda is an approximate eigenvalue of t, meaning that, for example, there is no number c such that you have this inequality, for example. For every vector on C0. This is what this limit implies, right? There is no lambda number c that makes this true for every x. Therefore, if this means that if this operator is invertible, the inverse is not going to be continuous. Okay. This also gives us some ideas. So give us more ideas on how we should proceed on this research topic. So we just proved that this sequence goes to 0, right? What if we prove that this sequence is convergent? Then that will imply that this limit, this vector, is an eigenvector for the compact self-adjoint operator corresponding to lambda. Like this, right? The details, well, this I think that is a standard, but let me show it. This if this limit is y, then when you use t, this means that the limit of lambda xk is y. This implies that if the image of the image is going to be ty, then we know that this is going to be just ty, yeah, by definition, by having this condition. So that is a proof that you will get, sorry, this will be lambda times, where is it? Oh, that's what happens when you start doing proofs on the spot. Yeah, you will have this equality. Lambda times I will be ty. Okay, so this result tells us that we can approximate eigenvalues of t using eigenvalues of operators of finite rank that approach to t, right? What about the eigenvectors? We want to prove that this sequence is convergent. And we are working in that direction, but it has been proven a challenge. So far, we just can prove the following. So consider the definition of B1 as before. Consider lambda 0 and lambda 1 eigenvalues for A0 and B1. That satisfies this condition. As the previous results showed, you always can find eigenvalues satisfying this condition. We just proved that if you have a vector, an eigenvector for B1 corresponding to lambda 1, you always can find a close eigenvector for A0 corresponding to lambda 0. This means that, and the difference is small, infinitely small. So this tells you that if you perturb the complex matrix A0 by an infinitely small matrix, you can approach the eigenvectors of A0 with eigenvectors of the perturbation, which is what you want, right? Then you want to generalize this problem to BK in general, that the eigenvectors of BK plus 1 can be approximated by eigenvectors of BK. But that is a work in progress right now. And I think that I'm on time. It's 11:51, so I will stop right here. I just want to say thank you. Thank you very much.
Thank you, Angel. Any questions? Comments? Okay, then let's thank Angel again, and